Hello and welcome to this lesson on nuclear instability, which is part of the nuclear physics topic in AQA A-Level Physics. So in today's lesson we're going to look at discussing the different types of radioactive decay. So if we've been successful and learnt in today's lesson, we can discuss what you can deduce about radioactive isotopes from an NZ graph, detail how a nucleus changes with radioactive decay, and then explain why naturally occurring isotopes do not emit beta plus radiation, which is part of the nuclear instability topic 3.8.1.4 in the AQA A-Level Physics module, Nuclear Physics. So in nuclear decays, nuclei change from unstable nuclei into stable nuclei. Now most processes have this carry out via the weak interaction. So in this case, the W boson is passed from the unstable nuclei to its more stable products. Now the decay process lessens the impact of the electromagnetic interaction and increases the strong interaction. The only exception to this is alpha decay, which doesn't involve leptons or particles changing type, so therefore it decays via the strong interaction. But once again, this decay process lessens the impact of the electromagnetic interaction and increases the strong interaction. So we've got this alpha decay occurring with a very fast interaction. Now in our previous examples we've considered radioactive nuclei to be an unhappy face. However, in reality it's more appropriate to say an unstable radioactive nucleus is like a bubbling volcano. It's constantly churning and turning, waiting to erupt and become more stable and emit a form of radiation. So a slight change in the energy or the configuration of an unstable nucleus will cause radioactive decay. But what causes instability and what interactions are found in the nucleus? So there are two interactions which affect the stability of a nucleus. You've got the strong interaction, which causes attraction between all nucleons in the nucleus, and the electromagnetic interaction, which causes repulsions between all the protons. So to achieve a stable nucleus, the strong interaction must be much larger than the electromagnetic interaction, because remember, in a stable nucleus the strong interaction must be a lot greater than the electromagnetic interaction, because the strong interaction causes attraction between all the nucleons, whilst the electromagnetic interaction causes repulsion between all the protons. Now nuclear instability occurs when the strong interaction and the electromagnetic interaction are very similar in size. Now it's important to note that if the electromagnetic interaction was larger than the strong interaction, the nucleus wouldn't even form. So every nuclear decay tries to increase the magnitude of the strong interaction compared to that of the electromagnetic interaction. Now a nucleus will become unstable if it either has too many neutrons, too few neutrons, too many nucleons in total, or just has too much energy. Now physicists were fascinated to see if there were any trends in nature to show which nuclei were stable and which were unstable. So physicists surveyed all known isotopes of substances on Earth, and from this they plotted an NZ graph. So in this graph the neutron number is placed on the y-axis and the proton number is placed on the x-axis. Now these values were considered as the number of protons and neutrons can show the strength of the strong and the electromagnetic interactions. So we can look at the stability of isotopes by looking at an NZ graph. Now remember, just to clarify, N is the number of neutrons, not the number of nucleons, while Z is the number of protons. So on this graph we can plot the NZ line, which is when the number of neutrons equals the number of protons, and it's just a straight line through the origin. Now on the NZ graph we can also show a belt of stability. Now the stability belt is the region on the NZ graph where there are stable isotopes. So for lighter isotopes the stability belt is where N equals Z, when you have the same number of neutrons as protons, whilst for heavier isotopes the stability belt is when N is greater than Z, so therefore there are more neutrons compared to protons. Now if an isotope is not in the stability belt, it will be an unstable isotope, and the region the isotope is found on the NZ graph shows the type of decay it will carry out. So it could be placed above the N equals Z line, beyond the N equals Z line, below the N equals Z line, and all these isotopes carry out different decays as they're found on different places on the graph. Now all unstable isotopes will decay to try and get onto the stability belt. So here's an example of the NZ NZ graph. Now most NZ graphs show a simplified version of possible radioactive decays, and they tend to focus on the beta particle emitters. This is because beta decay is the main decay carried out by the more common lighter elements. Now a more detailed NZ graph will show the stability belt for the isotopes, and that when a radioactive decay occurs, the isotopes shift towards the stability belt. So what trends can you spot on the NZ graph, and where are the different types of emitters of radiation? So you can work out the nuclear decay from the isotope's position on the NZ graph. So there are several types of decay modes that an unstable nucleus can undergo. Now alpha emitters occur beyond Z equals 60, most of them found at Z equals 80 or above. These nuclei are too large to be stable, as there are too many protons, so the electromagnetic force is too large as the strong force is too spread out in that large nucleus. Beta minus emitters are found to the left of the stability belt. These isotopes are neutron rich compared to the stable isotopes, whilst beta plus emitters are found to the right of the stability belt. These isotopes are proton rich compared to the stable isotopes, and this is actually the same area as which electron capture occurs as well. Now isotopes with too many protons compared to neutrons can carry out beta plus emission, or they can carry out electron capture. So electron capture is in competition with beta plus decay. Electron capture causes an outer shell electron to drop into the inner shell to replace the electron captured. This then carries out de-excitation and releases a gamma photon. Now it's important to note that gamma emitters cannot be displayed on this graph, as the number of protons or neutrons do not change due to this particular emission. But what are the different emission processes? So the first one is alpha decay. So alpha decay is when two protons and two neutrons are lost from the nucleus when it emits an alpha particle. So this means the atomic mass number decreases by 4 and the atomic number decreases by 2. So a new element is formed that's 2 places lower in the periodic table than the original element. So alpha emission is when an alpha particle or helium nucleus is ejected from the parent nucleus. Now this must mean there's a new element formed, since there are a different number of protons in the main nucleus. Now whilst alpha is the same as a helium nucleus, the term alpha is used if that particle originates from the nucleus of an atom. Now because we're forming a new element in alpha emission, it is an example of transmutation, and like mentioned before, the element is formed in alpha decay 2 places lower on the periodic table than the parent element. Now each alpha particle is released with the same kinetic energy as no other products are produced in the decay. So here's a demonstration of alpha emission. The next type of emission is beta decay. Now in beta minus decay, a neutron changes into a proton plus an electron. The proton stays in the nucleus and the electron leaves the atom with high energy as a beta particle. Now the atomic mass number in this case will stay the same, whilst the atomic number increases by 1. So in beta minus decay, the nucleus has 1 more proton and 1 less neutron when it emits that beta particle. So it can produce a new element 1 place higher in the periodic table. So in beta minus emission, a neutron is transformed into a proton that stays in the nucleus, and an electron and an antineutrino, which are both emitted. Now beta minus emitters are found naturally in the universe, and they can be manufactured when stable isotopes are bombarded with absorbed neutrons. Now again, beta minus is an example of transmutation because a new element is formed since there are a new number of protons in the nucleus. Now whilst a beta particle is the same as an electron, the term beta is used if the particle has originated from the nucleus. Now the element formed in beta minus emission is found 1 place higher on the periodic table compared to its parent nucleus. Now like we mentioned before, beta minus emitters are found naturally in our universe, and here is a demonstration of beta minus emission. Now beta plus emission is when a proton is transformed into a neutron and a positron along with a neutrino. So the opposite beta decay process occurs to beta minus decay. Now again, a new element must be formed since we've got a new number of protons in our parent nucleus, and the term beta is used because this particle originates from the nucleus. So this is another example of transmutation, but in this case the element formed is found 1 place lower on the periodic table compared compared to the parent nucleus. Now, beta plus emitters are not found naturally in the universe. They can only be manufactured with stable isotopes being bombarded and absorbing protons. Now, in gamma decay, there's no change in the makeup of the particles, they just lose energy in the form of photons. So alpha emission is often followed by gamma emission, and the daughter nuclei are left in an excited state from the alpha emission, and then at some point they fall from the excited state to the ground state, emitting a gamma photon. So there's no nuclear structure change, just a change of energy. So this is not an example of transmutation, as no new element is formed. So a nucleus which has excess energy before gamma decay is in what we call a metastable state. So here is a demonstration of gamma ray emission, and it's important to note that gamma ray emission will only occur after alpha emission. Now, the next type of nuclear decay is electron capture. So in electron capture, a nucleus can capture one of its orbiting electrons, and a proton then will change into a neutron, okay, and you will also get an emission of a neutrino. Now, this has the same overall effect as a beta plus emission. So again, it's an example of transmutation as a new element is formed. Now, also remember that when you carry out electron capture, you will also produce a gamma photon due to de-excitation, and a neutrino due to lepton number conservation. Now, electron capture does not increase stability for a nucleus as much as beta plus emission, but requires less energy to carry out the process. Now, electron capture will produce a new element one place higher in the periodic table than its parent nucleus. Now, another example of a decay is a nucleon emission. So it's possible for an unstable isotope to emit a nucleon from its nucleus. So for example, in a proton-rich or proton-heavy nuclei, it's possible for a proton to be emitted. So again, you will lose one proton. So again, this is an example of transmutation as a new element formed, and the new element is formed one place lower on the periodic table. Now, in the other type of nucleon emission is when you emit a neutron. So in a neutron-rich or neutron-heavy nuclei, it's possible for a neutron to be emitted. But this time, it's not a case of transmutation, as no new element is formed, as you have the same number of protons. And in addition to the traditional decays of the nucleus, there is also a sixth nuclear decay, internal conversion. So internal conversion is a process in which a nucleus is in an excited state and can release its excess energy. Now, in internal conversion, all of this excess energy is transferred from the nucleus to an orbital electron through the electromagnetic force. The orbital electron is then ejected from the atom. Now, both internal conversion and beta decay will eject electrons from the nucleus, but there are differences between internal conversion and beta decay. Firstly, beta decay occurs by the weak interaction, whilst internal conversion occurs via the electromagnetic interaction. Secondly, beta decays will also produce either neutrinos or antineutrinos in the process. And beta decay will also produce a nucleus of a new element, as you've changed a neutron to a proton or vice versa, but internal conversion does not. In beta decay, electrons are emitted with a range of energies because you're also producing a neutrino or antineutrino, but in internal conversion, because you're not producing a neutrino or antineutrino, all the electrons have the same energy. In beta decay, the electron emitted will be from the nucleus, whilst technically in internal conversion, the electron is emitted from the shell. Now, we can represent all these different decays, whether it be alpha or beta or electron capture or neutron emission, proton emission, internal conversion, with a decay path diagram. So this shows how the neutron number and proton number change in a decay. Now, in reality, an unstable nucleus will undergo a number of different radioactive decays before it becomes stable, and we can show this on a radioactive chain decay diagram, which is a chain diagram is each decay is linked to the previous decay for that particular nucleus. Now, it's also interesting to note that in a true decay chain diagram, there are a variety of decay paths which an unstable nucleus can take, and the path the unstable nucleus will take is down to probability. And in addition, a comprehensive decay chain diagram will also include the half-life of this decay process. as seen in this diagram on the screen now. So what have we learned in today's lesson? We should hope to be able to state the graph of N against Z for a stable nuclei. You should be able to have possible decay modes of unstable nuclei, including alpha, beta plus, beta minus, and electron capture, and also indicate the changes in N and Z caused by radioactive decays and a representation in simple decay equations. So if we've been successful in today's lesson, we should be able to discuss what you can deduce about radioactive isotopes from an NZ graph, detail how a nucleus changes with radioactive decay, and explain why naturally occurring isotopes do not emit beta plus radiation. So I hope you've enjoyed today's lesson on nuclear stability, which is part of the nuclear physics topic in AQA A-Level Physics. Thank you very much for listening and have a lovely day.